Hello everyone, I'm Bindu Trikha, Assistant Professor. I am Ms. Ghaziabad. In the previous video, we had learnt about sequential circuits, and in this video, we would be learning about SR flip-flop, or we can say it as a SR latch. Latch is a basic storage element and it latches 0 or 1. Like we have a latch for the door. When we latch the door, that means we lock the door, nothing can go into the room or nothing can come out of the room. Similarly, when the door is open, things can go into the room as well as things can go out of the room. Here also we have a latch, a memory element whose value is either 0 or 1. 0 means we have latched the door and 1 means it is open. A flip-flop is a latch with a clock basically. That is, logic gate would work with the clock pulse. That in say we are designing SR latch, we would not be using any clock. And if we are using a flip-flop, we were designing a flip-flop, we would be adding a clock to it, and our inputs would be working on the clock pulses only. In SR flip-flop, S stands for set and R stands for reset. SR flip-flops can be designed either using NOR gates or NAND gates. In this video, we would be designing the SR flip-flops using NOR gates. And in digital electronics, reset means output is 0 and set means the output is 1. Now this is the circuit diagram for a SR latch, or you can say SR flip-flop. If we add a clock to it, it would become a flip-flop. Herein we have used two NOR gates. We have NOR gate 1 and NOR gate 2. We have S and R as the inputs, where S stands for set and R stands for reset. And as I discussed earlier in digital electronics, set means 1. That is, if set is 1, Q would be 1, output is 1. And if reset is 0, the output is 0. Reset means to store the value 0 to the circuit diagram, and set means to store the value 1 to the circuit diagram. Here we have feedback paths as well. Whatever output we are getting in the form of Q and Q bar are going into the NOR gates as well as the current inputs also. Now we will discuss how this particular circuit works. Herein we have used the same SR flip-flop or latch, where we have two NOR gates, NOR 1 and NOR 2. We have the inputs as S and R and the outputs as Q and Q bar. The outputs here are, if one of the output is 0, the other output would be 1. And similarly, if one output is 1, if Q is 1, Q bar would be 0. So the outputs are complement of each other. Herein we have used NOR gate. So we would be first discussing the truth table for NOR gate. Let us design it. Say we have two input NOR gate. A and B are the inputs and Y is the output. Here we have 0, 0. If the values of input for NOR gate is 0, 0, the output would be 1. Otherwise, the output is 0. Now, case 1. Say S is 0 and R is 1. In this truth table, we can clearly see if any one of the inputs for NOR gate is 1, the output is 0. This can be used in the result of this particular SR flip-flop. Now since R is 1, irrespective of the second input to the NOR gate 1, the output for Q would be 0. Now if output for Q is 0, this 0 would go as the input to NOR gate 2. For NOR gate 2, we have two inputs 0, 0. According to the truth table, if the two inputs are 0, 0, the output is 1. So, if S is 0, R is 1, Q would be 0 and Q bar would be 1. That is a set condition. Now, we are saying that this is a memory element. So how can we prove it is a memory element? Yes, we have got the outputs. We have got Q as 0 and Q bar as 1 for this particular input set. But if I am saying that this particular latch is behaving as a memory element, this means that these values should be preserved. Say I am taking the inputs as S is equals to 0 and R is equals to 0. That means as long as the inputs are not being applied to these NOR gates, let us see what is the resultant values of Q and Q bar. If S is 0 and R is 1, that means this is the situation with us. Now here we see if the previous output Q is 0 and Q bar is 1, then this Q bar would be going as an input to NOR gate 1. And if any one of the outputs for this NOR gate inputs for this NOR gate 1 is 1, then the output for this whole NOR gate would come to be 0. That means the current output is 0. Here we have shown the previous output by red color and current output by blue color. Now this means Q is 0. This 0 would now be going to NOR gate 2. Herein we have two inputs 0, 0, which in turn would give us the result 1. That means Q bar for the current as a current output would be 1. Herein we can see when S is 0 and R is 0, the values of Q and Q bar does not change, they remain the same. That is, whenever the input is not applied to this NOR gate or this flip-flop, the the flip-flop behaves as a memory element. This means it is a memory element because values of Q and Q bar are not changed. Let us take into consideration second example, that is case 2. In case 2 we have S as 1 and R as 0. If any one of the inputs for NOR gate is 1, the output is 0. Thus the output for NOR gate 2 would be 0. This 0, this is Q bar, and then this means Q bar is 0. Now this 0 would be going to NOR gate 1. Now here both the inputs are 0, 0. That means the output for this NOR gate 1 would be 1. That is Q would be 1. That means your flip-flop is in set state. Now let us here also we can test whether this particular circuit is working as a memory element. If we want to test it as a to be working as a memory element, we need this S and R to be both to be 0. So this is the situation with us. S is 0, R is 0. The truth table for NOR gate is mentioned and the previous values for Q are 1 and Q bar is 0. The value of Q now goes to NOR gate 2. We know if one of the inputs for NOR gate 2 is 1, the output becomes 0. The output with blue color is the current output. This output now goes to the NOR gate 1, wherein the inputs are 0, 0 giving us the output as 1. Thus q is 1. So here also we can see that the values of q and q bar does not change, they remain the same. Whatever values we have, whatever output we were getting earlier, the same output we are getting at the current time. That means when s is equals to 0 and r is equals to 0, this particular flip-flop works as a memory element. That means it latches the value. If it has q is 1 as 1, it would remain as 1. If q is 0, it would remain as 0. Now we come to the third case, that is when s is 1 and r is 1. Now here we know that when one of the inputs is 1, or for the NOR gate is 1, the output is 0. This means Q bar is 0 as well as Q is also 0. But this is contradictory. Q and Q bar cannot be 0 at the same time. That means this result is unacceptable and impossible, so we don't use this particular condition with SR flip-flops. And the condition s is equals to 1, r is equals to 1 is never used with SR flip-flop, and it's a limitation for SR flip-flop. Now based on the various cases we have discussed in the particular SR flip-flop, we come out with a characteristic table for SR flip-flop. Herein we have taken QT as the past output, S and R as the values of the current inputs, and QT plus 1 is the current output. Now when S is equals to 0 and R is equals to 0, whatever the value of QT was there, it would remain same. That means it would not change. That is, it behaves as a memory element. Now we come to row number 3 and row number 4. We have S as 0 and R as 1 in both the cases, and the QT plus 1 would be 0 for both the cases, that is reset state. When we have S as 1 and R as 0, the output for the current state would be 1, that is a set state. And the last one, S is equals to 1 and R is equals to 1, we have already discussed that these states are not used, undefined, reason being that Q and Q bar both cannot be same at the same point of time. If Q is 1, Q bar should be 0, and if Q is 0, Q bar should be 1. But here we are getting the same values for Q and Q bar, so this state is undefined. And this is all about SR flip-flop. I hope you must have now known about the basics of SR flip-flop and would do it well. Thank you and have a nice day.